All right, today we're going to talk about molecular structure for covalent bonded atoms. This refers to the geometric shape or the three-dimensional arrangement of atoms in a molecule. For example, water has a bent structure with a 105-degree angle between the two hydrogens on the oxygen. Some molecules, such as carbon dioxide, have a linear shape. Atoms are in the straight line. There are two simple theories to describe covalent bonding. We're only going to talk about one today. The other is something you would learn in freshman level college chemistry. The one we're going to talk about today is called valence shell electron pair repulsion, also known as VSPER. The other has to do with the hybridization of those orbitals, S and P and whatnot, and that's for like freshman college level chemistry. Okay, so we're only going to talk about VSPER today. So we talk in terms of the electron density around central atoms, and they tend to be arranged as far apart to minimize repulsion. Remember, electrons are negatively charged, and like charges repel, and opposite charges attract. So atoms tend to form a shape that naturally reduces the repulsion. And atoms are three-dimensional, even though here today I'm only going to show you two-dimensional pictures, but I'm going to do the best I can to show you some three-dimensional structures. And they move around in space, so they're not like in a fixed place. So there's 5 basic shapes that we'll look at with variations of those. Now, the key here is that it has to do with electron density, meaning bonded and non-bonding pairs around a central atom. That part is key, okay? Very key. Electron density around the central atom. That's what we're actually looking at in order to understand these shapes. So if we look at a central atom with 2 regions of electron density, either bonding or unbonding, we would have a linear shape. So here's some central atom, here's electron density, and these are bonding, okay? So in this case, there's no lone electrons on the central atom, and you have 180. So from here to here is 180. And we call this the stickball method of modeling things, okay? The other is if you have 3, and this makes a trigonal planar. Planar meaning it's up in a plane. They're all in the same plane together. And these are 120 degree angles. So there's your 120. So this is some atom with 3 either bonding or unbonding electrons, pairs or atoms around it. 4 makes a tetrahedral. So again, these are going to be spaced out so that they have the least amount of repulsion. Now notice these shapes here, okay? This is important. There's a central atom and 4 electron densities, either bonding or unbonding. This indicates that it's coming at you. This indicates that it's going away. So this gives us the perspective of the three-dimensionality of it. And tetrahedral meaning 4, and then any of these around the central atom is going to be the 109 degrees. So even these 109 degrees, so on and so forth. If you had 5, gets a little more complicated. Again, they try to space themselves out. Notice it's trigonal bipyramidal, so we go back to that planar trigonal model here, okay, and where you've got those the 120s in between here. We also have 90s. We have a right angle here. See that right angle? There's a right angle. And then, of course, the 180s. So you can kind of think of it as a linear with a trigonal planar smashed together. And 6 makes octahedral. Again, you have these 90s, which are between these 2 atoms. You can see that 90-degree angle there. And then in between, we have those 180s. Okay, and there's a 180, there's a 180, and 180. And then there's variations of each of those. So we often talk in terms of electronic geometry, which has to do with electron density. And that can be either bonding or unbonding electrons. So either atoms, and talking in terms of atoms, or just lone pairs of electrons. But we can also talk in terms of the arrangement of the atoms, and we call that molecular geometry. Okay? Electron pairs are not used in molecular geometry. So you'll get to see both of those. All right? This is handy because it gives you, again, some examples of some common compounds that would form this particular electronic arrangement or this molecular shape. Okay, so we've got linear, molecular shapes also happen to be linear, so like boron trifluoride, boron tetrafluoride, you've got trigonal planar, still called trigonal planar, and then you also have methane, tetrahedral, and then here now we have unbonded pairs of electrons. Now notice the electron shape is very different than the molecular shape. And then we draw it on paper to indicate what the shape looks like. So it's called a tetrahedral. There's 4 electron densities, but there's 3 bonding and 1 lone on the central atom. Here there was 4 bonding and no lone on the central. Here there was 3 bonding and no lone, and here there was 2 bonding and no lone. So here there are 4 electron densities, but 3 are bonding, 1 lone. So what that actually does is it decreases the angle between the unbonded and the bonding, and we call it trigonal pyramid. So what happens is this lone pair of electrons actually has a greater repulsion and has a greater occupied space than those electrons of the hydrogen in, for example, ammonia. Okay? A variation of a tetrahedral is also what's called bent, or like water. Again, these lone, it's still got 4 electron densities with 109 degrees, but the actual molecular is called bent, and there's 2 lone pairs on the central atom. So these actually take up more space and have greater repulsion, thus the angles of these are slightly less than 109. And there's another nice picture with some other examples. And then these are the hybridizations, which we won't talk about. This one's nice because you get to see the variations on where these electrons are. We can talk in terms of these others, but we probably won't. These aren't as, these are for like more complex molecules that you would learn like in, again, freshman college chemistry. And then polarity. That's an important part of this because you get to understand polarity in this point. You know, here this is nonpolar. This is an example of nonpolar. If all of these are not all bonded, that would be an example of nonpolar. But as soon as you start introducing non-bonding pairs, you start creating polarity. So these end up becoming polar compounds. Okay, so you can have seesaw, T-shaped, linear, square, planar, square, pyramidal. Okay, and here's another example. This one I like the best because it says 2 bonding with no lone pair. See this? 2 electron density with no lone pairs on the central atom. Okay, and then you don't even talk about these guys unless you talk about like things like hydrogen diatomics. Then you can talk in terms of hydrogen being bonded to hydrogen. I'm not talking about these up here. Ignore this for a second. And then this would also be an example. So all of your diatomics, I think I'll talk about that here in a minute in the notes, but all your diatomics end up being linear. Okay, let me erase. Okay, back to my pen. Okay, so again, 3 electron densities about a central atom with no lone pairs, trigonal planar. Replace one of those bonded atoms with lone pairs, and now you end up with these angles that are a little less than 120 because this takes up more space and has greater repulsion. Okay, down to 4 electron densities. Again, the little wedge indicates it's coming at me through the screen. The little dash lines means it's going away behind the screen. If we have 4 on a central atom with no lone pairs, tetrahedral, remove one of the bonded atoms with lone pairs of electrons, we end up decreasing this bond angle because of the repulsion of the lone pair, trigonal pyramid. Remove another bonded atom, you end up with what's called bent, which is water. And then more complex ones, which we don't really have to cover these, but they're kind of interesting to look at. Most high school chemistry stuff all involves these guys here. Okay. Again, this is where I talked about molecules only having 2 atoms are linear, and there's no bond angles. And that just kind of is common sense. If you just have 2 atoms, they're bonded, and you know they're linear. And then these examples, this is a nonpolar, 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 but polar electron density unshared equally. So very positive, very negative. Okay, so the other thing I want to show you is this handy dandy little website. And for some reason it says that my graphic quality isn't so great. I don't know why. I'm going to show you both the molecular and electron geometry. And these little ball and stick means a bond and some atom. 2 bonds and some atom. 3 bonds and some atom. This little balloon with eyes, it means like a lone pair. And we're going to show the bond angles. So this is kind of a fun website to play with, because you can actually rotate it around and put it into any kind of orientation you want. So molecules don't just float around in space in one fixed thing, or in your body, or anywhere else in the universe for that matter. They always are moving, okay? So this is kind of neat, because even if you try to force them into an angle of less than 120, because of the repulsion, they want to go away, okay? And they still make the 180, all right? So let's just look at if we remove and replace them with a double bond. Does that change the bond angle? Nope. So guess what? The number of bonds don't really change the angle. So let's add a triple. Doesn't change the angle, okay? Even if we remove that and add another triple, still doesn't change. So the number of bonds between the bonding atoms on the central atom doesn't change the angle at all, okay? So we can add a lone pair, and we can remove that, still linear. Okay, so that would be an example of hydrogen, well, a cyanide ion, for example, where this is carbon and that's nitrogen. All right, so let's remove all of these, and I'll go through and add. So there's our linear. Let's add the third one. Now this is trigonal planar, and see why I say it's planar, because they're all in the same plane, X, Y, and Z. Okay, remember we're talking 3-dimensional here. So they're all in the same plane, so you can arrange it in any kind of order you want here, position rather, not order. Okay, so we're going to add another, and we got a tetrahedral. All right, so we can make it even orient so that, see how this is coming at you? I'll even move it a little more this way, coming at you, going away, and you might even, you know, say that this is in the plane if I can get it in the right angle here. Okay, but what happens when we remove one and add one? Now we have ammonia, okay? So ammonia has this unbonded pair in H3, and then these bond angles slightly decrease right here, okay? These are slightly decreased, all right? Or we can remove that and we can make water. And then this is an example of bent with 4 electron density, 2 unbonding, and 2 bonded, and then this angle decreases just slightly. Okay, so now I want to show you some real molecules. So there's water again. I'm going to show you the electron density and the bond angles. And you will see this one is slightly less than 109. So this is the real molecule of water. Okay, OHH. So this ends up taking more space, causes this to bend down more because the repulsion is greater. All right, let's look at carbon dioxide, linear. Okay, here's carbon, and then oxygen, oxygen, 2 double bonds, and no lone pair. So 2 electron densities and no lone pairs on the central. And then let's look at sulfur dioxide. So you wouldn't have probably thought sulfur dioxide had the shape of being bent and being a trigonal pyramid, trigonal planar, but it is. It's trigonal planar, 3 electron densities, 2 bonding, 1 lone pair. This is the sulfur, and this is oxygen, oxygen. So you can see how that changes, and you've got these electrons here. So if we take away, I can't take away the oxygen, so the lone pairs I was going to show you. a lot of times the lone pairs aren't shown in others. Let's look at ammonia, another example of a tetrahedral but trigonal pyramid. So again, these get bent slightly down, less than 109, because again, this is a greater repulsion, these lone pairs, nitrogen, and the 3 hydrogens attached. And you can adjust this position anywhere. Another common compound you might know is methane, which is a tetrahedral. So it's carbon, 4 electron densities, tetrahedral with no lone pairs, and these are all 109 degrees in all of those angles. Sulfur hexaoxide is an example of an octahedral. So you get to see how all 6 of those, this violates the octet rule when we talk about Lewis structures, which I don't really get to show you much of because I don't have a way to, but if you see this ends up with more than an octet, 2, 4, 6, 8, 10, 12, and it's called a expanded octet, and so sulfur tends to violate the octet rule along with phosphorus or examples of others, and there are some compounds of covalence of transition metals that will also violate the octet rule and have expanded octets. Let's see, I think that's about all for you to look at, and you can play around with this yourself too, but that's kind of a nice way for you to be able to see these bond angles and how they don't really change in their shape, and they try to stay as far apart as possible. Okay, and I'll be sure to add this link along with the notes here for you to access it if you'd like. All right, talk to you later. Bye.